Okay, our next presenter is Eric Markwith. He is also a thesis student, and his advisor was also Professor Min-Chang Lee. Eric?
All right, good morning, friends. So, my name is Eric Markwith. My advisor for this work is Professor Min-Chang Lee, and the title of my project is kind of a mouthful, but it is Investigation of Enhanced Ion Lines in HF Heater Wave Injection Experiments at Gakona, Alaska. So, there's a pretty significant amount of background information I'm going to go through at first. The purpose of this experiment is to investigate the low frequency band of a certain plasma instability, which I will discuss later, and to develop a theory for received signals from during Gakona, Alaska experiments this summer during at the HARP research facility during SSRC 2011. So the main background topics are parametric decay instability and an ion acoustic wave cascading process. I included a level 1 block diagram just to, make it easier to explain how this process really works. You have a transmitted wave that you select the frequency of the transmitted wave based on how you want to heat the plasma, which is based on altitude and local plasma frequency. It excites this instability, and the enhancement mechanism, which is what my theory is aiming to describe, and then the frequency of the ion acoustic wave and the mirror radar beam are convolved to get an output power spectrum centered at approximately the center frequency of the mirror radar. So parametric decay instability, it's a plasma instability, which is just a turbulence that can occur due to changes in the plasma's characteristics, which will occur based on the selected frequency of the transmitted wave, and they can include magnetic field fluctuations, temperature, and density gradients. The PDI that we're going to excite is excited through O-mode heating, which, if you have any questions on that later, I can explain that as well, but I've left that out of this presentation because there's a lot of background information. So this is the O-mode heating. Basically, the key characteristic is this electric field that is perpendicular to the background magnetic field, which in this experiment is the Earth's magnetic field. And this is also the geometry of the O-mode waves, where you can see how the electric field and the K vector are related to the background magnetic field. So this is a diagram for parametric decay instability. It's a three-wave interaction where you have your transmitted wave represented by omega naught in the frequency matching relation, and a high frequency band and a low frequency band, with omega L being the high frequency band, it's called a Langmuir wave, and omega IA being the ion acoustic wave, which is what I am investigating during this during these experiments. Also, I've included a wave vector matching relation, which can be seen through both relations can be seen through this this diagram here. Mainly the wave frequency matching relation, which, as you can see, the omega naught is simply a sum of omega 1 and omega 2, where omega 2 is the frequency of the Langmuir wave and omega 1 is the frequency of the ion acoustic wave. And these matching relations come from conservation of energy and momentum. So how we excite PDI is you select the frequency of your heater wave, and that should be selected at approximately the frequency of the local plasma at the altitude that you want to excite the instability at. Right here, we're looking at F region plasma. During the experiments that I ran in Gakona, Alaska, this frequency I think was about 4.3 megahertz. So we select 4.3 megahertz as our Keter wave so that we can excite parametric decay and stability. The reason that you pick the frequency of the transmitted wave to be approximately that of the local plasma frequency is to overcome a threshold for PDI that's set by collisional damping. So the normal modes that are excited by PDI are two electrostatic waves, and as I explained before, they're called the Langmuir wave and a non-acoustic wave, one being a high frequency band, which is basically a plasma wave, a plasmon, and an ion acoustic wave, which is in the audible frequency spectrum, so it's called a phonon. Both modes are electrostatic waves, and the goal is to overcome collisional damping so that your wave can actually propagate down the magnetic field and can be detected by the mirror radar. So there's actually problems with detecting these ion lines. You have to make sure that they are, when I show you the data that we processed later, you have to make sure they're out of the thermal noise level, because the thermal noise level will be in approximately the same frequency range as the ion acoustic waves that you're trying to detect. Also, because the ion acoustic waves have a large radar cross-section, if you can actually detect space debris by accident, but we know that it wasn't the case in our experiments because we use basically a quasi-continuous mode heating. So we're getting data every 5 seconds, and if you were detecting space debris, it would just pass over because we're transmitting waves vertically up the magnetic field. So these Maxwellians actually represent a collision-less damping that only affects the ion acoustic waves, because normally you would have your particles would be distributed as a normal Gaussian between particle distribution, particle density, and phase velocity. But when your phase velocity is approximately the same as the velocity of your of the transmitted wave or the Langmuir wave, they can effectively interact with that wave so that energy can actually, they're called resonant particles, and they can actually steal energy from the system because they act at the resonant frequency of the wave that you produce. So this cascading feature is really what was, this was explored by Laura Burton, but she focused mainly on the high frequency end. My project focuses on the low frequency band. Her project mainly was looking at a cascading feature. So what's happening is you can actually get several cascades of PDI at the same altitude because you're transmitting at a frequency close to the local plasma frequency, and since your low frequency band is only a few kilohertz, the Langmuir wave that's produced is going to be on the same order of magnitude as at peak plasma frequency. So as long as the collisional damping is still overcome, you can still satisfy this threshold for PDI and actually excite many cascades of PDI at the same altitude until that frequency matching relation is no longer satisfied. So that's what I have on this slide, and right here I'm just showing that when you're looking at the subscripts, the 1, the 2, they are the first generation and second generation. So what I have on the bottom is actually, that's a little bit smaller, is actually more important. Omega naught should be the sum of the first Langmuir wave and the first ion acoustic wave. And from omega naught minus the first Langmuir wave being the frequency of the ion acoustic wave, you see that since the ion acoustic wave is at such a low frequency, the matching condition can still be satisfied for this for the instability that we're looking for at that same altitude. So I did this proof for this beta parameter, mostly to prove that it's much less than 1, because in controlled fusion experiments, you can basically set your beta parameter because you have a lot of control over the environment that you're working in. But this environment is practically just an O+ plasma. It's in the F region, so you can this summation of the particle pressures just ends up being one constant particle pressure, and the magnetic pressure can also be determined based on the background magnetic field as well as the permeability. So this is magnetometer data during my experiment. So this is included because the experiment was run during turbulent conditions, mainly in the presence of the electrojet, because what we were initially looking for was a very strong field-aligned current to drive these Langmuir waves to produce an asymmetric spectrum, which I'll show you later. And using this MATLAB script that I wrote over the summer, you can plot these frequency spectrums. So let me just, here's the actual data. So what you see here is practically it's the power spectrum of sine cosine wave. You see some basically delta at plus and minus the frequency of the ion acoustic wave, which is about 1.5 to 2 kilohertz. You see like a double hump feature from like thermal noises from Doppler spreading, and the thermal noises that are happening at the bottom around 3 are from particle precipitation. That is based on rheometer data that's included in my thesis, but is not in this presentation. So the key feature of this that we're looking at is this. You see the frequency upshifted component, which corresponds to received Langmuir waves, is for this whole time period it's about 1.5 to 2 times that of the lower end. Theoretically, if you just detect these ion acoustic wave signals, you should see a double humped feature, and both should be approximately the same magnitude, because you're just receiving one wave of one like sine cosine wave. You're sending something up, you should be getting the same thing back. So what I have here is, this is actually the final stage of development of my thesis. So I've actually started looking at the Langmuir wave as the source for this asymmetry. Even though the asymmetry is associated with the ion acoustic wave, it's the Langmuir waves that actually will increase the energy of the system, because they are the waves that are at a higher enough frequency to actually interact with the plasma at that altitude. So what I have here is the dispersion relation for these Langmuir waves, and we're looking at also the product of the group and the phase velocity. So the second part of this comes from just taking the derivative of the top part, and you see that you're looking for something that's 3 times the thermal velocity squared. The thermal velocity is the electron thermal velocity at that altitude. We can approximate that because typically the energy of an electron at the altitude that we're looking at is about 0.1 eV. So what we're looking for is whether or not the produced Langmuir waves will be able to actually accelerate electrons downwards, down the magnetic field, in order to enhance this power spectrum that we see. We observed for actually several nights during the electrojet at Gakona, Alaska. So what's important is that this relationship is met. So the phase velocity is pretty simple to calculate, because we know the approximate frequency of the Langmuir wave as well as the cross section, and based on that we can find the phase velocity, and based on the last expression we know that the phase velocity times the group velocity should be approximately 3 times the thermal velocity squared. And the thermal velocity is estimated using the approximate energy of electrons at the given altitude. So what I've also this is more of a this is what I looked at the very end. This is more of like a future work for this. So I actually had a crude model made for the for this relationship that I've shown you to calculate the approximate group velocity based on just basic force equations, force energy equations using electric field divided by charge and setting that to 1/2 mv squared. But that model doesn't give us an accurate picture because you find that you only get a thermal velocity of something on on an order of magnitude of 10 to the 4, which is not enough for effective particle interaction to happen. So the next thing to look at is ergo enhancement, which has been observed at this altitude in previous papers. It's a red-green ergo enhancement that corresponds to about a 2 eV to 4 eV local plasma energy enhancement. This comes just from wavelength of red-green air glow. So what we're looking for now is whether or not that 2 eV difference is enough to effectively excite this bulk electron acceleration down the magnetic field. But as I said before, the model that I did make for this system wasn't working because of collisionless Landau damping that occurs in the ion acoustic waves. So what we're looking for further is a more sophisticated model that can actually include the Landau damping growth rates. So as a final note, the way that I'm actually planning on continuing this, like polishing up the end of my thesis a little bit over the summer. What we're looking for is a quasi-DC field in order to effectively interact with bulk electrons. So what's important here is that the one wave period of the Langmuir wave is enough time to effectively excite this 2 electron volt difference in energy. So that is what I'm going to continue my work on. So it is, this also, I used a pretty crude model for this that didn't really give me produce the results that I had expected, but I'm looking for a more sophisticated kinetic energy analysis in order to explain this. So further analysis is, as I said, just see if this 2 eV difference corresponds to enough energy to actually excite any bulk particle acceleration down the Earth's background magnetic field. And acknowledgements, I just wanted to say thanks, Professor Lee, for taking me to Alaska and giving me the opportunity to do all these experiments, and for all the help on the thesis. And questions?
The results of your analysis, do they indicate the need for additional experimental data to validate the results?
Oh, ideally, yes. I would like to see the we would like to see the same trend reproduced in experiments next summer. I mean, I won't be there, but we're hoping to get more data that agrees with this. We did see it, like, there were 2 different nights that we did see something kind of similar.
All right, thank you.